here. You know, you've got the snow plows on the bridge, putting salt on everything. Yeah. Well, how did the problems for homework go? Any issues? They're okay? So no one needs me to go over anything? Because I'd like to move into the next section, but this was a pretty important section, so okay. No. No? All right. Then we're going to move Yes. Yes. $197. Number 9. Natural log x over x. Okay, natural log x. So limit, that's not limit x goes to 0 from the right of natural log x over x. I can see why this would be confusing. So first of all, what happens to the natural log function as you approach 0 from the right? It goes to negative infinity. And then the bottom goes to 0, but it goes to 0 through positive numbers, so I'm going to put a little plus on the top right. This is not an indeterminate form. Okay, indeterminate would mean infinity over infinity or 0 over 0. So just think about what's happening here. Your numerators are getting bigger. Your denominators are getting smaller. So what happens if I have, let's say, a fraction, and I have the top keeps getting bigger and bigger and bigger? What happens to that number? If the bottom stays the same and the top gets bigger, what happens to the fraction? It gets bigger, right? So this is getting bigger. So if the bottom were staying the same and the top was going to infinity, this thing would go to infinity, right? Negative infinity. Let me put negatives up there. So that would head towards negative infinity, right? That's only if the top was getting bigger and bigger and bigger. Now, separate idea. If I have a fraction and the bottom starts to get smaller, where does that go? That goes to infinity, right? Because these fractions start up as 2, right? This one, 4 divided by half is 8, right? This is 32. That's 400. That's going to infinity. So what's happening here is these two guys are actually helping each other out. The top is like, I want to make this fraction bigger, and the bottom is like, well, I'm going to get smaller, which is also going to make this bigger. So they're working together to head towards infinity. It's negative infinity because the top is negative. That makes sense? So there's really not any work that you could do here. If you like, see if there's another way I could write that. Another way you could maybe reason this out is like this. Just rewrite that problem this way. As 1 over x times natural log of x, which is the same as natural log of x over x, right? Now, what happens to 1 over x as you go to 0? Well, fixed over 0 is going to go to either infinity, negative infinity, or does not exist. But the fact that I'm approaching 0 from the right means these are little positive numbers. A fixed number over little tiny positive numbers, or 1 over a little tiny positive number, is going to be a huge positive number. So this is headed towards positive infinity. Then times, what do we say this is headed towards? Negative infinity. If you multiply positive infinity times negative infinity, you get negative infinity. That making sense? Okay. So either way, you can look at it this way or you can look at it this way. No problem. All right, so now 4.2? We won't be in this section very long. The mean value theorem? The mean value theorem comes actually from another theorem called Rolle's theorem. Did I talk about Rolle's theorem in the video? Any of you who watched the video before this? No? I know. You've given up. I was thinking about that. I think I was thinking about that at some point recently. That I hope those videos still hold some value. Okay. I got you. Okay, so here's the idea. Rolle's theorem says this. Let's say that you have a function that, is it 0? That's defined on a closed interval like this. So let's say at A, you plug in the value, it spits out C. And I tell you that at B, it spits out C also. And then in between, I don't really care what it does, except for the fact that I'm telling you that it's continuous there. So F is continuous. On AB, means you can draw it without picking up your pencil. I'm telling you that F of A equals F of B, which equals C. So the function's value is the same at the beginning as it is at the end. Oh, and can I change this C to a D? Is that all right? It's not too hard to change that to a D. Change that C down here to a D for a reason. I want to follow kind of what the book says here. So because the two endpoints are the same, I'm going to connect it with a straight. I'm going to connect the endpoints with a straight line, and that's just a flat line, right? That line right there has a slope of 0. If the function satisfies that, then this should be true, right? That line is flat. Do you agree that there's at least one place, somewhere in between A and B, where if I look at the derivative, which is the slope of the tangent line, it's flat? Right? It looks like up here, there's a slope of a tangent line that's flat, and it looks like down here, there's also, right? So I'm going to call this point that it happens C. I'll call it C1, and I'll call this one over here C2. So Rolle's theorem says that if this is true, okay, if this right here is true, you have a continuous function on a closed interval, you have that the two endpoints give you the same value, the result of Rolle's theorem says this. Then, here's the result. There exists at least one C in the interval AB. There's going to be at least one point in here, at least one. And it's also important to note that that point that I'm talking about is inside the interval. It's not at the endpoints. It's somewhere in there, right? Somewhere in there, there exists some point such that, how do I say that? That this derivative, the slope of this will be the slope of this. Such that the derivative of the function at C will be equal to what? The slope of this line? What's the slope of this line? 0. Won't that always be 0? Like if the two endpoints are the same, I connect them with a straight line, that's always 0. Slope of that line is 0. So there's at least one point in there where the slope is 0 also. Does that make sense geometrically that that would be the case? You think that there's a way that you could draw something where that wouldn't happen? I mean, try it yourself. You have a function does this, right? Good. Good, good. So what about a cusp? That's continuous, though. This is continuous because I can draw without picking up my pencil. So is this condition of being continuous strong enough? What do you think we also need? Not only is it continuous in here, what's wrong at this point in here? What can't I do right here? The derivative doesn't exist here, right? Remember at a cusp? So not only, for this theorem, not only do you need that it be continuous in here, you need it to also be differentiable inside. All right, so good point. I'm going to add that to it, but let me see if there's anything else we can come up with here. What about this? Would this work? It's not continuous, right? Okay, so I violated. So that's why we have to have the continuity. Because the derivative along this line segment's fine, derivative over here is fine, derivative at there is not defined, but it's also not continuous. So up here, with this condition I'll put in red, f must also be differentiable. I'll put DIF, f, on the interval, and it only has to be differentiable on the inside, but so we throw that out, that can't work. We throw this out, it can't work. Go ahead and try it yourself. Try and draw something, and you don't need to do it now, but just if you try and draw something where you have to connect 2 points together and you have to be continuous and differentiable, there's no way to draw it where that's not going to happen, where you're going to get a slope of tangent line equal to 0. Yes? The catenary? That would work. Yeah, because look, if I did the catenary here and draw it right like this, then the point that it would occur would be right there. That slope of that tangent line would be equal to the slope of this line. These two slopes are the same, right? I was just saying it's a different curve. Like if you see a wire hanging between two poles, you may think that that's a parabola. It's not a parabola, it's a catenary. It's a different function that draws that. That's all I was saying.
So then could you say that the slope between the endpoints would always be a c that matches it?
The slope between the endpoints, exactly. That's exactly where we're headed with this. See, right now this is saying that if we have two endpoints, right, the slope between them, which in this case is 0, there must be somewhere in there where the slope here is equal to the slope here. So, but we start usually with Rolle's theorem. The title of this section is what? The mean value theorem. We start with Rolle's theorem because most people can put their heads around this idea that if you have 2 points, you draw a straight line here, slope of that 0, then there's some place where the derivative must be 0. Now we get to the mean value theorem. The mean value theorem says, just imagine rotating this picture. Just rotate it. So mean value theorem, which I'm going to call MVT from now on, says this. Here's the picture that goes with mean value. You do not have to have your two endpoints come up with the same value. That doesn't have to be the case. And your curve inside is still continuous and differentiable. So F is continuous on AB. F is differentiable on the inside. And that's all you need. Okay, you do not need the endpoints to be the same. It's obvious that they're not, right? But let's do what Tyler, right? What Tyler suggested. And that's, think about if we connect these two together, right? These 2 points, if we connect them together, there is some slope there, right? Do you see that there's got to be somewhere on our curve, somewhere where the derivative will be parallel to that? I think it's happening somewhere around here. Looks like the slope of the tangent line would run parallel to that line. And there looks like there might be another one somewhere around here. So in this case, it looks like there's 2 places. Now, it just so happens the way I'm drawing my pictures, we keep getting 2. What the mean value theorem and what Rolle's theorem guarantees us is at least the existence of 1. All right? So, but how do I say this? In the last one, all I had to say was, look, the slope somewhere, right? The slope, the derivative somewhere is 0, because we knew that this slope was 0. Do you know what the slope of this is? Not right offhand, do you? It looks like 1 here, but I need to come up with a better, more precise definition of what that slope is. So let me get to this. So if this is true, then here's the conclusion. How did I say this? There exists at least one C in AB. Okay, here's the way math people would write that. There exists a C element of AB. All right, that's the same thing as saying there exists a C inside the interval AB. Capital E backwards, have I shown you all this notation before? Okay, capital E backwards means there exists a C. This symbol is element of, means contained in this set. So there's a C in that interval, such that, our symbol for such that is just usually ST, okay? Such that what? The slope of the tangent line at some point here, right? I'm going to call this C. The slope of the tangent line there, which I would write, the slope of tangent line is the derivative at C, right? That's the slope of tangent line. At that point, I'll label this one red up here, right? We need that to be equal to what? That should be equal to the slope of this line connecting these 2 points. Well, what's the slope? If someone gives you 2 points, what's the slope of the line between 2 points? Rise over run? Or y2 minus y1 over x2 minus x1? Remember that formula? Well, this point has the coordinates a, f of a, and this one has the coordinates b, f of b, doesn't it? Like, I don't know what A is, and I don't know what B is. I don't know what F is. But if I did know what A, B, and F were, then those would be the coordinates of those points. So this derivative at that point C should be parallel or equal to that slope, which should be F of B minus F of A over B minus A. And that is the mean value theorem. Rise over run should be equal to the slope of the tangent line somewhere in there. Right? If you just turn your head, that's Rolle's theorem, isn't it? Just turn your head. That's Rolle's theorem. Okay, let's see how we can apply the mean value theorem to something. Verify the mean value theorem for f of x equals x cubed minus 3x squared plus 4 on the interval -2, 3. So it's just saying to verify the mean value theorem. It's telling me that I need to show that there exists at least one point inside this interval where when I take the derivative at that point, it should be parallel to the two endpoints of this curve at these two endpoints, right? Like it should be parallel. So yes, that's what I need to show. I need to just show that that's true. I'm verifying everything's good. Well, let's start off with the conditions we need. To verify the mean value theorem, we need what? Our function to be continuous on the interval -2, 3. Is it? Yes or no? Okay, why? Because it's a polynomial. All polynomials are continuous everywhere. So it is good because it's a polynomial. All right, is f differentiable on the interior of the interval 2, 3? Yes, because what's the derivative of that? 3x squared, blah, blah. It's a polynomial also, right? It's well-behaved. Polynomials are really nice to work with. So, well, I should say the derivative is a polynomial. So therefore, it's differentiable because the derivative is nice. And that's all you need for the mean value theorem to hold up. So once I've verified those conditions, what I need to show, so I want to show, I'm not just being lazy, like these are things that math people use a lot, WTS, want to show there exists a C inside where? -2, 3, the open interval. I have to show that there's a number inside -2, 3. It can't be at -2, can't be at 3. It's got to be somewhere inside. I want to show that there exists a C in there such that the derivative at that C, which I don't know yet, is equal to f of b. What's b for me? 3. F of 3 minus f of a. What's a for me? -2 all over b minus a, which is 3 minus -2. So f of 3 and f of -2 is just what I get when I plug 3 into the function, and then when I plug -2 into the function, I subtract those. So let's figure out what this is, and we'll talk about this side in a second. And also keep in mind, the way that we do these, we work with this, it's like left and right hand sides we're going to move down together, okay? Like, just watch. Let's figure out the right side first. So f prime of c must be equal to, plug 3 into this function. 3 cubed, 27, take away 3 squared is 9, times 3 is 27 again, then plus 4. So you get 4 when you plug in 3, right? So I get 4 up here, minus, now plug in -2 into the function. So what's -2 cubed? -8. Then I go minus 3 times -2 squared is 4, and then plus 4. So what do we have there? -16, right? -16. Be careful, it's minus -16. And then over, what's the bottom? 5. Which is, we need f prime of c to be equal to 20 over 5, which is 4. All right, that's what I want to, I want to show that there's going to be a c somewhere in that interval, -2 to 3, where when I take the derivative there, it's going to give me 4. So at this point, can you just tell me what the derivative of this function is if I plug c into the derivative? So what's the derivative of this function? 3x squared minus 6x. But replace your x's with c's. So 3c squared, right? Minus 6c. That's the derivative, but just replacing the x's with c's. Yes? I need that to be equal to 4. That's what I need, right? And now this is a quadratic equation. And how would you solve that quadratic equation? I don't know, however you would solve it. Now I made this problem up, I just made it up, so I don't think that's going to factor. So you'll have to use quadratic formula. So I'll go ahead and do that here. My solutions are C equals negative B plus or minus the square root of B squared minus 4 times A times C all over 2A. So you get some answer, right? I should have brought my other calculator. I get one answer is 2.527. I'm getting a decimal answer. I could get an exact answer if I wanted to by just doing 6 plus or minus, let's see, what's the inside of that? Yeah, it's square root of what? 84? Root 84, and we'll just leave it like that, all over 6. So if you figure out what those are on your calculator, you're in business. There's two answers there, right? There's what happens when you take the plus and then what happens when you take the minus. So the square root of 84 as a decimal is 9.165 blah, blah, blah. So 6 plus or minus 9.165 all over 6. So that's why one of those answers was 2.527. The other answer, working on it, .527, something like that. Negative .527. Those are my answers, right? There were two solutions. That means there might be two places that it actually happens. Now, what you have to do is you have to check to make sure that both these C's live inside of the interval. So go back up here. What was my interval? Negative 2 to 3. Are both of these answers between negative 2 and 3? Yes. So these should both work. Those should both work. Now, if one of them was outside the interval, I'd just scrap it. Okay? The other one would be my answer. Mean value theorem says, though, at least one of those answers must be between negative 2 and 3. What if it's not? You messed up. Okay? Somewhere, either the function wasn't continuous to begin with, or differentiable, or somewhere in your algebra something went off, or maybe something in your derivative was off. But the mean value theorem guarantees the existence of that. Okay? So do you think you could handle these problems in the book? I mean, there's not a whole lot more to this. You check that it's continuous and that it's differentiable. Then you work out the right side. You work out the left side. Set them equal. I see some looks of, do y'all have a question? You want to do something a little more complicated? Sure. How about this one? Verify the mean value theorem for f of x equals cosine 2x. Although this one's not really that interesting to me. Seeing if there's anything more complicated. On 1 negative pi over 8 to 7 pi over 8. All right, is f continuous? It's a cosine function. It's continuous everywhere. What's the derivative of cosine? Negative sine. That's a continuous function. So it's continuous and differentiable everywhere. So I'm happy with that. So what I want is to show there exists a c somewhere in here such that what? The derivative at c is equal to f of what? F of 7 pi over 8 minus f of pi over 8 over 7 pi over 8 minus pi over 8. So remember, I'm using the fact that we're given the a and the b, the endpoints of the interval. This right here is f of b minus f of a over b minus a. That's always going to be the same in every one of these problems. Your right side of the equation will always be f of b minus f of a over b minus a. The left side will always be f prime of c, always. For mean value theorem. Now you do have to plug 7 pi over 8 into that function up there. So if I plug that in, I'll take this a little slower. I'm looking at the derivative needs to be equal to cosine of, what happens if I plug 7 pi over 8 in for x right here? It becomes 7 pi over, if I double this, right? It becomes 7 pi over 4? Yes? Okay, so that's really 7 pi over 4. And then minus, if I plug in pi over 8 into this, double it, it becomes pi over 4. Then all over, what's 7 pi over 8 minus pi over 8? 6 pi over 8, which is the same as 3 pi over 4. Questions? What is cosine of 7 pi over 4? Oh, hold on. We don't need a calculator. Hold on. Unit circle, right? When you're on the unit circle, cosine of the angle is equivalent to the x-coordinate of the point on the unit circle at that angle. So I need to figure out where 7 pi over 4 is. Pi over 4 is a quarter of the way here, right? That's pi over 4. This is 2 pi over 4. This is 3 pi over 4. This is 4 pi over 4. This is 5 pi over 4. This is 6 pi over 4. And this is 7 pi over 4. The point here is what? Root 2 over 2, negative root 2 over 2. So cosine is the x-coordinate. It's this. So cosine of 7 pi over 4 is root 2 over 2, which is what you got on your calculator, right? Okay. F prime c must equal root 2 over 2 minus. Now, how about cosine of pi over 4? Is the same thing, root 2 over 2. This time you go to pi over 4 and you look at the x-coordinate. It's root 2 over 2. Oh, isn't that nice? Isn't that special? Because what's root 2 over 2 minus root 2 over 2? It's 0. So all I want to know is when the derivative is 0. Big deal. You still with me? What's the derivative, but then replace x with c? So what's the derivative of cosine of 2x? Negative sine of 2x times 2, so that comes out, you get negative 2 sine 2x. That's a little bit of chain rule in there, right? That looks almost identical to a problem I gave on my pre-calc test last Monday. Find the solutions to that trigonometric equation. And I'm sitting there trying to explain to them why it might come into play later. Well, today's later. So can I take that equation and divide both sides by a -2? Okay, and just get sine 2x is 0? Yes? Now let's see how comfortable you are with trig equations. Let's see if you learned them in a way that's going to be beneficial to you. The proper way to solve this equation is to find a general solution, which means again, I like to go back to the unit circle. And when I'm talking about sine, instead of the x coordinate, I'm now looking at the y coordinate, right? I'm trying to say to myself, to get sine to be 0 means I need to go to the angles where my y coordinate is 0. So that would be here and here. Do you agree at those two places the y coordinate is 0, which means sine is 0 there? What are those two angles? 0 and 180. Now I'm going to stick in radians, because radians is like, I don't know if this is really a fair assessment, but if you were talking to someone, you said, hey, what's 12 divided by 4? And they wrote down 12 divided by 4, and then another person wrote down 12 divided by 4. Which of these people do you think you would feel more comfortable with as far as being decent at math? This one. Well, same thing with degrees and radians. When people want to stay in degrees, it's almost an indication of their fear of radians, and that's, you want to get comfortable. I'm not saying that whoever said degrees, I'm not saying that I'm calling you out or anything. I'm just saying you want to be comfortable with radians to the point that people don't recognize that it's a weakness of yours, You want to be really okay with it. Be able to switch it up, no problem. So back to this, it was 0 and 180, or pi is what we're going to go with, right? 0 and pi. But 2 pi would have worked also, right? And 3 pi. And 4 pi. And 5 pi. So the proper way to get a solution for this is to start at one of the solutions, doesn't matter which one, and see if you can get to the other one by adding something. So can I get to here by adding something? Yeah, add pi, right? Well, can I get back to this one by adding the same thing? Add pi again. And then can I get back again, pi? So it looks like these two guys are just off by pi. So now what I say is that I need the angle inside, which is actually 2x. I need the argument of the trig function, 2x, to be equal to, well, 0 radians, which is this point right here. But I could also add any multiple of pi. And the way we write that is pi k. Or some books said pi n, where k is an integer here. So k can be 0, k can be 1, 2, 3, 4, 5, 6, or k can be -1, -2, -3, -4. So that really means 2x could be equal to just k pi, or pi k. And now that means x could be equal to what? Pi k over 2. This is what we call the general solution. The general solution. I forgot to switch to C. Why didn't y'all tell me? It's okay. Don't worry about it. It's pretty common to forget to put the C in there. I'm trying to verify the mean value theorem if we've lost sight of where we were here. I'm trying to show that there exists some C. In this case, it's going to be X because I forgot. Somewhere in here that makes this thing true. I said that the thing that makes this true is anything that looks like this. So give me some examples of some answers here. Like if k is 0, what's the answer? X is 0? Does 0 live in this interval? No. Okay. So let k be 1 now. Try another answer. If k is 1, what do you get? Pi over 2? Does pi over 2 live in this interval? Yes? Yes. How can you tell? Why? It just is? See, it's obvious for some people and not for others, so I'm just going to point it out. Pi over 8 is the same as 1/8 of pi, right? 7 pi over 8 is 7/8 of pi. Yes? I wanted to know if 1/2 pi was in here. Okay. Which is 1/8 smaller than a half? Yes. Is 7/8 bigger than a half? So basically, the pi's don't matter. You just look at the coefficient in front. So 1/2 is between there. So yes, that is a solution. Is it the only one? Well, let me try k equals 2. If I plug in 2, what do I get? X is pi. Does pi live in here? Well, pi means 1 pi, doesn't it? And 1 is bigger than 7/8, so that wouldn't work, right? 7/8 is too small. So the only answer we have is at pi over 2. And as verification of this, if we put cosine 2x and we lock the interval between pi over 8 and 7 pi over 8, there's our graph, okay? And remember we said that when we found that slope on the right side, do you remember we said it was 0? You can tell because look at the endpoints. They're the same height. So if you connect these 2 points here with the straight line, ours should be parallel somewhere in there. Oh, it was right there, wasn't it? What did we get for our answer again? What did we get? Pi over 2. So if I type in pi divided by 2, yeah, look, right here. That's it right there. It's parallel to that, the one connecting the 2 endpoints. You'll see that? Okay. That better? You feel okay with that? All right. All right, so this is a problem I like to share with Cal 1 students when I get to mean value theorem. Why do they call it the mean value theorem? When we say the mean of something, what do we mean? Get all pissed off? No? Mean is average, right? So when you look at a function and you say, okay, let's say at this point, let's say at 2 it was 5, but then let's say at 7 it was 10. The average value, the average is, one way to look at it is this. If at 2 hours I was 5 miles from home, and then at 7 hours I was 10 miles from my house, then what was my average speed? Well, how far did I go? 5 miles, right? That's the distance I went? That distance right there is 5, right? That's the distance I went. How long did it take me? 5 hours, right? So it was, the average was what? 1 mile an hour, right? 1 mile per hour was my average speed, right? 1 mile per hour was my average speed. But isn't that 1 mile an hour also the slope of that tangent line? Okay? So the average value of the function is the slope of the line connecting the 2 endpoints. The mean value theorem says that somewhere in there you will have an equivalent. Your slope of your tangent line will be equivalent to your average value. Somewhere in there it's guaranteed. Now, here's what I like to share with people. Do you cycle? Did someone say something about gears? Oh. Oh, okay. 1 mile an hour on a bike is practically impossible. You probably fall over. Right? You couldn't keep your balance. So if we have distance on one axis and we have time on another axis, wrong way, time here, and let's go in hours, and we go distance here, and we go in miles. Then if I have a curve here, let's just start at the origin to make it easy. Then the slope of the tangent line, gosh, that's terrible, but you get the idea. The slope of tangent line, right, is our instantaneous rate of change at that point. And the units will be, do you remember if we have distance in time, the first derivative is what? Velocity, right? Your speed, basically, right? So the slope of this line, the slope of that line is your speed. That's really what this is saying. So tell me, right there, that point versus this point, at which point am I going faster? The first one or the second one? Second one, I'm going faster because I'm actually steeper, right? And then here, what's happening here? I'm going backwards. My velocity is negative. So that's like if I'm trying to race from here to that wall, and I start racing at positive speed, and then this is going to be negative speed, and then back to positive speed. You wouldn't do that, but I'm just saying, like, that's what that negative slope means. It means you're moving backwards. Okay? Y'all with me on this? If you have position and time, derivative is velocity. Now I get to the question I would love to ask my students. You have a race. This is looking from the top. Here's the starting line. Here's the finish line. You have, I don't know, two cars. Car A, car B. I'm not promoting. This is a closed course, right? All safety regulations. Did you hear that high school senior killed himself the other day driving 100 miles an hour on the access road? Yesterday? Yesterday? I don't know. I didn't read the whole thing, but flipped the car, burned up. Anyway, 100 miles an hour. All right. Okay, so look, here's what I'm going to tell you. The clock starts, and these two cars start racing, right? And then they come to the end, and it is a perfect dead tie. I know that's impossible, but let's just say they start at the same time, clock starts, they go, and they come to the finish line, they tie exactly. All right? So here are my questions for you. All right, here they are. First question is there a speed both cars had to attain? Any speed. But listen, the question is saying, is there some speed that both cars had to attain? Like, and not talking about the ends, okay? Forget, not at the ends. Okay, so of course at the beginning of the race, they're both at a standstill, right? They're both going 0. And maybe at the end you believe that if they cross the finish line at the same time that they have the same exact speed at that moment. Forget the ends. Somewhere inside the race, is there some speed that they both had to achieve? Do you think so? Okay, so there is, so you're saying maybe 1 mile an hour, and they both had to achieve that speed. So at some point one of them was going 1 mile an hour, the other one was going 1 mile an hour, right? So there was at some point, driver in car A did see 1 mile an hour on his speedometer, and at some other point, car B driver saw 1 mile an hour at some point in time. So there is some speed that both of them had to attain. Okay, these are questions I'm just asking you to think about. Okay, is there a speed both attained at the same moment? Question. And not talking about the ends again. So if they started and tied, is there a point in time, we all agreed that there's got to be speed that they both saw that on their speedometers. My question is there a specific speed guaranteed? Is there some? Does there exist? You can kind of see where I'm getting with this mean value theorem. Does there exist a speed somewhere in there where they both had to be going that speed at the exact same moment in time? So you have an argument for no, yes, yes, no. You don't know what they're. Okay, so look. So this is why I like to show this example. Yes. No, just an instant in time. Okay, but they both had to be going a speed at the same moment in time. So we're driving along. Your car driver B. So hold on. Right. So you're back there, and I'm up here, and there's some moment in time as we're racing that we both look down our speedometer, and at that exact same moment in time, exact moment, we both are seeing the same speed on our speedometer. Guaranteed it has to happen, yes or no? So I've heard yes, I've heard no. Okay, well look, the thing about this is we could argue about it, and we could have opinions and all this stuff, and then we could bring in the math and just bring it to rest, okay? So let me draw a picture of what's happening. Let's draw a picture. Okay, since they both started at time 0 and ended at time, I don't even know, can we just call it, well, let's call this A, and let's call this B, all right? Let's call it A and B. They both started at some point on a starting line. Now, it makes sense to say 0, so let's say 0. That's where they started. This was our distance. This was our time. So car A does this. Drives, does something, I don't know. It gets to a certain distance, right? And stops. As time goes on, it's driving, there's a certain distance, yes? Now, I'm going to exaggerate car B a little bit just to make things interesting. Like that, okay? You see that? No, A and B, no, those are capital A and capital B are our cars. Little a and little b is our interval of time, just to make it match up with Rolle's theorem. And wow, my B is way off. Let's make B be the end, okay? So what I'm saying, if you look at it this way, is there a moment in time where their speeds have to be the same, where the slope of the tangent lines have to be the same? Is it guaranteed? Does it look like there's one here? Maybe. Do you think that I could draw it where it would be impossible to have it happen? So again, I'm still trying to get you to see, like, what is your brain telling you? What is your logic telling you? What's the math going to tell us? Yeah. And your title's on the line. Your girlfriend's going to kick your ass if you don't win. All that stuff. Everyone's going to tweet that you're a total shit. I mean, I don't know. What are all the precious kids have these days, right? They measure themselves. Their value is measured on how many friends they have. Okay. Okay. Keep it down. trying to maintain some professionalism up here. Okay, so let's do this. If we all agree that both of these curves are continuous functions, meaning that car A is not going to vanish off of the racetrack and then reappear somewhere else, right? It's continuous. The speed is defined at every point, so the derivative exists at every point, right? We all agree on that? Then I'm going to create a new function out of this. This A, this A function, it may as well call it F, and this B function may as well call it G, just so it looks like stuff from before. Do you agree with me or not that if I define a new function, I'll call it H, to be F minus G, that it's just the difference of the two functions? That's okay? Now, is H still continuous? Well, we had a theorem way back that said if you take two continuous functions and you subtract them, it's still continuous. And if you take two differentiable functions and subtract them, it's still differentiable. I would like for you to tell me what H looks like geometrically, though. I'm going to try and get this all on one page. What does H look like? At A and B, tell me what H is. At A, what's H? What's the difference between these two functions at A? Nothing, right? Zero difference. What's the difference between these two functions at B? Nothing. And then the rest of it has to be connected with a continuous curve, right? And I could care less what it looks like. But, I mean, it looks like the difference between them is kind of small in the beginning, and then it gets a little bigger, right? And then it gets smaller, and then it gets bigger, but then it closes down. Something like that, right? Who cares? It's a continuous function, right? Can I apply Rolle's theorem to this? Is this a continuous function on closed interval? The two endpoints are the same? And you told me that you believed Rolle's theorem guaranteed me a point, didn't it? There's some point in here, C, such that what? By Rolle's theorem, there exists a C somewhere in the interval AB such that the derivative of what function? What function is that I graphed? That's H, right? The derivative of H at C must be what? In this case, because it's Rolle's theorem, 0 because the endpoints were the same. Yes? But what is the derivative of H? Remember, H was what? F minus G? So if I say what's the derivative of H, I'm really saying what's the derivative of F minus the derivative of G. What's the derivative of F minus G? You do them separately, right? Just, this side of the equation is really F prime C minus G prime C equals 0, isn't it? Move the G prime to the other side, and what do you have? F prime of C equals G prime of C. So what we've said is that there exists a C inside AB where the derivative of C of F at that point is the same as the derivative of G at that point, but the derivative of F and the derivative of G is exactly the speed, right? The speed. So there is a point somewhere in there between A and B, somewhere after the clock started, somewhere before the end of the race, where at that exact same moment in time, both cars were going the exact same speed. It's guaranteed by Rolle's theorem. But you had to do this kind of clever thing of realizing that you could define a new function as the difference of the two functions to get a real clear perspective on what was happening. They start at the same place, they end at the same place. That's the key to the whole problem. If they didn't tie, it's not guaranteed. But the fact that they tied forces us to have a point in there where the speeds were identical. So there's no debate about it anymore. Okay, it's guaranteed. I like that illustration because it really kind of shows you how you can use math to solve problems that you have people that are debating their, you're sitting there and you're trying to rationalize and make it, no, and people have good arguments both ways, and you're like, yeah, I kind of see it like that, but and then eventually you just get to the point where you're like, look, let's put an end to that, right? Trust the math. I'll give you another one of those sorts of problems just that are kind of counterintuitive. Have I shown you the one where you're filling up the cup? The cup? The beer? Not the funnel. Okay, so like in a perfect world, let's say I have a perfect container. Perfect container that holds exactly 1 cup, whatever the heck 1 cup is. All right? It's empty. I'm going to start filling it with water. All right? And the first thing I'm going to do is I'm going to put 1/10 of a cup. I have a way of measuring exactly 1/10 of a cup. And I pour it in there, right? So there it is. Here's 1/10 of a cup in there. Here's my 1/10 of a cup inside here, right? And then I come in there after I've done that and I pour in 1/100th of a cup. So I measure out 100th of a cup. And now I pour that in there. It's not quite as much, right? But it's in there. And then I come in, I do it again. Right? And I do that forever, following that same pattern. So 1/10, 1/100th, 1/1000th, and I keep doing it forever. So I'm adding this to this, to this, forever and ever, never stopping. My question to you is, does the cup overfill? No. So there's one answer. Anyone think it overfills? No? it's I start out with 1 cup. I put in 1/10 of that cup. Then I follow that by 1/100th, then 1/1000th.
Okay, so you're splitting 1 cup of water up.
No. I have an empty cup, right? And then I have over here a big container of water. And I measure out 1/10 of a cup exactly, and I go pour it into the empty cup. Then I measure out 1/100th of a cup exactly. I pour it into the cup that I just put a tenth in. And then I come in here, I do it again, and I do it again forever, ever, and ever. They get smaller each time. So the question is, does it overfill? These do get smaller, I agree. These are getting smaller. But, so this is where I was saying counterintuitive. One side of you might be saying, well, he's asking this because it's not obvious, maybe. But then the other part is, look, real quick show of hands. How many of you think that this will overfill? Don't be ashamed, okay? Okay, you think it'll overfill. I think the logic is pretty simple if you think it's going to overfill, because look, this is a positive number, right? It's something bigger than 0. Then I'm going to take that, I'm going to add to that another positive number, and then another positive number. So each time I'm adding something. In the vessel, the container is finite. So how is it possible that you can sit there and add, and keep piling something on top, right, without actually overfilling? That would be my argument for it's going to overfill. Wouldn't that be kind of your argument too? So how many of you think it's not going to overfill? Okay, why not? Because these are smaller. Now look, it's purely theoretical here. We are not getting down to like atomic levels here and saying, but you can't split the water at some point. Look, it's purely theoretical. If it was possible to put 1/100000th of a cup in there, you could do it. So from a purely theoretical standpoint, what's your argument that this doesn't overfill? Okay, but you're kind of on the fence. And it's a very simple problem to show you that it doesn't overfill. All right? So just think about this. What is 1/10 written as a decimal? Okay, plus what's 1/100th written as a decimal? 0.01. What's 1/1000th written as a decimal? 1/10,000? And if you start, and you keep doing that, if you start adding those forever, you get what? 0.1111 forever, right? Which if you do that on your calculator, that's exactly 1/9. So if you do 1 divided by 9, you get 0.1111 forever. So not only does this cup not overfill, it doesn't even get halfway filled. If you could do it forever, which you can't, but if you could, the further out you go, the closer you get to 1/9. A tenth is not as big as a ninth, right? So you put in a majority of it went in right away, right? And then the rest of it didn't do a whole lot to add to it, right? So are you convinced that that wouldn't overfill, or kind of? I mean, it looks like it mathematically, theoretically, but yeah. What if you're drinking it? All right. So maybe it was because they were getting smaller, right? So what about this? What if I take in 1/2 a cup plus 1/3 a cup plus 1/4 a cup plus 1/5 a cup, and I keep doing that forever? Is that going to overfill? Let me do a couple more. 1/6. Is that going to overfill? They're getting smaller, right? So look at this. Just put those two together. What's 1/3 plus 1/4? Get a common denominator. 7/12. Isn't that bigger than 1/2? 6/12 is 1/2. 7/12 is even bigger. So you had 1/2, and then you put in 1/3 and 1/4, and now it's over full, right? This right here, just these three, is bigger than 1. So that's just those three is over a cup. So believe it or not, I mean, what you're doing right now, what I'm talking to you about right now, not to get ahead, but since I know some of you were discussing this earlier today. No. Whoa, what is that? Here we go. This is it right here. Right there. This is Cal 2. This is my lecture I did on the other day in Cal 2. What is the sum? What's 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 forever? Okay? This is called a geometric series. So what I'm getting at is that, I mean, what am I getting at? I'm getting at there are a lot of problems in mathematics in the real world where you don't necessarily want to trust your intuition. Your intuition can lead you to the wrong place. A lot of times people say, just go with your gut, go with your gut. That's true unless you're building a bridge. If you're building a bridge that people are going to be, their lives on the line, you don't go with your gut, you back it up with some, yeah, that feels strong enough, yeah, that'll hold. Right? I mean, it's crazy. It's crazy out there. These people that, I'm one of those people where when we hire people to do stuff, I pay too much attention. Like we had for our homeowners community, we had these big shade structures put in, right? Huge shade structures, and they lagged them into the concrete, right? So the guy comes out, and like I've already like done computations myself on like what I think the load's going to be because it's like cantilevered out there and stuff. And so the guy comes out and he pulls out the bolts, and I'm like, what's the shear strength on the bolt? And he's like, what? Yeah, I mean, he didn't know anything about it. He's like, these will hold, man. We've been putting these in for years. Like, he didn't know anything about them, which isn't necessarily his fault because he's probably just the installer. That's fine. I mean, whoever engineered it. But, I mean, the fact that they weren't, they couldn't give me any specs or refer me to anyone, I'm like, I mean, they should know. They're putting them in, right? They should know. And then also they have to know, like, the strength of the concrete. And then they're putting it in, and there's, like, they don't even check the depth of the concrete to know how thick the slab was. Like, so if you're putting a bolt that's, like, super strong in 4 inches of concrete, it doesn't matter how strong the bolt is. You're going to rip the concrete out, right? So, like, all these things, and I'm just like, you're bonded, right? You're insured? Good, because anyone dies, it's not coming back on me, But I pay too much attention to these things. I don't trust instinct of people. The instinct of people when it comes to things like that, not good. All right. Let me see if I can get back to the right class. Is this where we were? Okay. We're done with mean value theorem, I think. It's a nice result. As far as what you would see on a test, it's not a whole lot. I mean, there's not a whole lot of material that I can test you on other than to give you a function, ask you to verify mean value theorem, be done. So for homework off of this section, look at page 215. 1, 3, 9, 11, 12. I'll just point out that the first one and the third one, that's Rolle's theorem. 9, 11, and 12 are mean value theorem. It says it in the instructions. It says, for 1 and 3, it says, show that these functions meet the conditions of Rolle's theorem, and then show what Rolle's theorem's conclusion is. The 9, 11, and 12 are, verify the mean value theorem. All right, that brings us to 4.3. This is a big deal section. Derivatives and shapes of graphs. What we're interested in right now is seeing how these derivatives that we've been looking at all semester somehow help us in determining what a graph looks like. What we studied in 4.1, not 4.2, but in 4.1 we said that if we had a function on a closed interval, right, closed, that we could always find the absolute max and absolute min. That's what you did in your homework last time, right? You just find the critical numbers wherever those happen. You take those points, you take the endpoints, you plug them in the function, you compare, right? That was the method. So we know how to find the highest and lowest points on a graph if it's on a closed interval. Now we set forth trying to figure out how to figure it out if you're not on a closed interval. So no more restriction on your domain. So closed interval. Thank you. Thank you. Closed interval method is good, right? We got this. This finds the max, the min, right? We've done that. So let's look at a graph of something where I'm not going to close the interval off. Okay. Ugh. That didn't quite work out the way I wanted. There we go. Good enough. Now I put an arrow at the end of this, like this, and I'll put an arrow on the other end like this. Whenever you see arrows at the end of graphs like this, it means that we have to kind of like agree that we mean it's just going to continue doing that in that direction. So like what I mean by this arrow over here is it's just going to continue to go down this way, okay? And then over here this arrow is going to continue to go down. It's not going to do some crazy thing and come back up, all right? So does this graph have an absolute maximum? Yes. An absolute maximum, it does. It has a highest point on the graph. Does it have an absolute minimum? Can't tell. It looks like this goes down forever, then it's going to not have a lowest point, right? Because every time you think you're at the lowest, this graph keeps going down. Same thing on the other end, right? Doesn't look like it has an absolute minimum. Does it have a local minimum? Yes, right here, right? Does it have a local maximum? Looks like there's one over here somewhere. And we've discussed this before, so this isn't brand new. We said that there's usually very interesting things happening where these points are, right? Like what's happening to the derivative right here at this blue point? What's happening here? The derivative is 0. What's happening to the derivative here? Does not exist, or it's undefined, right? What's happening here? Derivative is 0. But there was also another point where the derivative was 0. It was right here. But that wasn't a maximum or minimum, was it? So we had to be real careful. I mean, it's like, just because the derivative is 0 does not mean you have a max or min. Yeah? because it kind of comes down like if you were the tangent line here, you come down and then you would flatten out just for an instant, and then you would keep going like that. Okay, so let me now see if I can get you to understand this idea of increasing and decreasing. If everyone's okay with that. All right, let's imagine that we are riding this roller coaster, all right? And we'll just read it like we read a book from left to right. So if I'm on a roller coaster here, we're going up, right? So it's up, we're increasing, and then we get to the top, and then it's, and everyone's all happy. And we're going down, right? What happens here? Flatten out for just a second, but then as soon as I get past that, what's happening? I'm still going down, not very quickly, but I'm going down. That's it. That's a bad roller coaster. That's the end. Sorry about that. I didn't warn you all before the ride. Okay, so here we have a major catastrophe. But then we start what? We're going down, and we go back up, and then top, and then back down, right? So the idea of increasing and decreasing is just like a roller coaster, up or down. Are you moving up or down as you're moving from left to right? So I'm going to split this picture up into the places where I'm going up and the places where I'm going down. So let's see. Where am I going up? How about over here? Am I going up over here? Yes. Remember, we're reading it from left to right. I know it's going down, I'm saying, but if we were on it, we'd be going up. Where else am I going up? How about over here? Like that? I'm going up right there? Anywhere else I'm going up? No? Where am I going down? Here. And then even over here, right? And then over here. Okay, the yellow parts of this graph is where we say that the function f is increasing. And then over here, increasing. The blue parts are where we say that f is what? Decreasing. Now, I don't like to write increasing and decreasing over and over and over because I think it's too long of a word. So instead of writing f is increasing, I will write f with the little arrow like that. And when I mean decreasing, I will write f with the little arrow coming down. Notice those arrows are not straight up and straight down. There's a little bit of a tilt to them because I am assuming we're going from left to right. So going up and then coming down. Is that all right if I use that notation? So we said that at the highest and lowest points, these interesting places, that the derivative was always doing something there, right? It was either 0 or did not exist, right? What can you tell me about where I'm increasing? What about the derivative? Tell me about the derivative in the yellow. It's positive, right? Positive, 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 until I get to the top at 0. Over here, positive, 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 positive. What about where I'm decreasing? What's the derivative? Negative, right? Slope of tangent line, negative, negative, negative. Now it comes to 0, but then negative, 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 right? Do you think that there's a correlation between the derivative and whether or not a function is going up or down? Absolutely. That's what this is all about. The derivative actually tells us the shape of the graph. It tells us if it's going up or down. So I'm going to put over here, when I say that f is increasing, I'll put it below this. F increasing on some interval I, so I is going to be an interval, means the derivative is what? Positive. How do I say that? Greater than 0 on I. If I say that f is decreasing on an interval I, that means what? The derivative must be negative on I. That makes sense? All right, so let me now force you to look at some situations here. We'll get into doing problems in a second. I really want you to try and get this visually first. I'm going to look at a couple of scenarios. Everyone agree that that would be a maximum? Yes? What's happening with the derivative up here? The derivative is 0. What would be the derivative on this side? The derivative would be positive. Can I just do plus instead of greater than 0? What would the derivative be on the other side? Negative. Do you think that we'll be able to determine it's a maximum by investigating the derivative on both sides? Look at this one. That was one where we had the issue where the derivative was 0, right? But it wasn't a max or a min, right? It was not a max or min. What is the derivative to the left? Positive. What is the derivative to the right? Positive. What did not happen? It didn't change. You see that? We went from increasing to a derivative of 0 and then kept increasing. There was no change in the derivative there. Here, we went from increasing, right? Everyone's getting anxious, and then all of a sudden, everyone's happy, and we're all going, change in derivative over the peak. Even at a cusp, look at a cusp. Now, what's happening with the derivative here? Doesn't exist. However, what's happening as far as increasing? The derivative here is positive. Over here, it's negative, right? So we still have the whole concept of we went up, we came down. The function was defined here. The derivative didn't exist. How about at low points? How about at low points like this? What's the derivative there? 0. Uh-oh. Wow. I think that's probably the first time that's done that. Okay, I lost that drawing there. Okay, so how about here? What's the derivative here? 0. What's happening to the left of it? It's decreasing. I'm trying to match my colors. So over here, the derivative must be negative here, right? And then over here, the derivative would be positive. So again, you see the switch from positive to negative? It happens. And that's how we are going to check to see if we have found a max or a min. That's how we're going to check. We're first going to find out where the function's derivative is 0 or doesn't exist. And then what we're going to have to do is just check something to the left and check something to the right and see if we get the change in sign on the derivative. If that happens, we'll be able to conclude it's a max or a min. With me? That's right. If it doesn't change, there's no confirmation of it. Now, there is another thing that we'll do that'll make it a little easier, but you can't always use it. It's called the second derivative test. And, well, we'll get to that when we get to it. All right? That's a minimum, yeah. Derivative is 0 at the point. To the left of the point, the derivative is negative. Right of the point, it's positive. That's local only. Yeah, we won't be able to find absolute max and mins on open intervals easily because we don't know. We can't check. We can just see everywhere that we're having these little humps or cusps happening. You got it? Okay. You're okay with it? All right, good. Is there something I could say to help everyone else get it that made you understand it? Or? That's right. If it's going up and then down, it's the highest. Down and then up, it's the lowest. Now, we do have to be careful for things like this. All right, we haven't addressed this, but look. What about a function that did this? All right, what's happening at this point right here as far as the derivative is concerned? It doesn't exist. The function doesn't even exist, right? Over here, though, what's the function doing? It's increasing, right? So the derivative over here would be what? Positive. Over here, the function is decreasing, right? So the derivative over here would be what? Negative, right? So you might think, oh, look, to the left of this point, it's positive. To the right of this point, it's negative. So it goes up and then it comes down. You may think, I've found a maximum, right? The difference is that this function is not defined at that point, as opposed to this one, where your function had to be defined for this to happen. See, the derivative doesn't exist here, right? It goes up, then it goes down. That's almost the same as this, right? The derivative doesn't exist here. It goes up and then down. How are you going to tell the difference? Well, the fact that this one is not even defined there. The function itself isn't defined. That's going to be able to let you throw it out. But it's subtle, right? And it's dangerous, so we have to be careful. So the first derivative tells us about where we go up and where we go down. All right? That's what it tells us. The second derivative also gives us information about a graph. And here's what it is. F double prime, well, you know what? I'll do pictures again. I'm going to mark off, we have some local max and local mins here. If I were to split this up to where it's increasing and decreasing, I've been using the yellow and the blue. It would look like this. Do you all agree with that? That would be my derivative is positive here, my derivative is negative here, my derivative is positive here. Over here in this little region, derivative was negative, right? Okay, that's what I would have. The first derivative tells us up and down. The second derivative has to do with something called concavity. F double prime determines not up or down, this thing called concavity. Concavity comes from the word like concave. I've heard like concave mirrors or concave, I don't know. You've heard concave before? Convex, concave? All right. So concavity is not up or down. What it has to do with, it's real simple to break down if I try and like not dumb it down, but make it as simple to understand as possible. Most graphs that are nice and smooth and continuous either look like a part of a smile or part of a frown when it comes down to it. The curve is either part of a smile, right? Can you all see the smile? Right? It's either part of a smile or you're part of a frown. That's what concavity is. It's which one of those. So if you are concave up, if the graph is concave up, then it's going to look like the smile. If it's concave down, it's going to look like a frown. Now, the second derivative is what tells you which one of these it is. The second derivative, if it is positive, you're concave up. If the second derivative is negative, you are concave down. And you can remember pretty easily. Positive people tend to smile and negative people tend to frown, right? So let's look back at this picture right here. and tell me where we have, let's try and see if we can determine where we have a frown, I think. How about from that top point? I don't want to write on top of my blue and my yellow. What do you say over here? Are we frowning over here? Am I frowning? How far down do I go, though? Do you see that there's this like weird point somewhere around here, somewhere around here? Do y'all see that right around there we have this kind of interesting point where the frown actually turns into the smile? The asshole becomes kind of cool, like finally is okay with life, everything's good, right? So look, right at this kind of juncture, now you're smiling. And you're smiling and smiling and you're smiling over here. I don't know what's happening over there. But you see, the frown met the smile, right? At that point, right here, that point where that happened, guess where that is? That's where the second derivative is 0. Because, look, I told you to be concave down, the second derivative had to be negative. So in that pink area, it's negative, and then all of a sudden, it's positive, right? Well, to go from negative to positive, you have to pass through 0. So that's where you change your emotion. Yes, very emotional point occurring there. And we actually have a more technical name for it. It's called the inflection point. The inflection point. Now, I had another inflection point. You see it? It was over here on the left side. That's where that frown over here turned into a smile. And it actually is a smile over here, too. So if I tell you that a function is concave up, can you tell me if it's going up or down? If all I tell you is that a function is concave up, can you tell me if it's going up or down? Right here. This is all concave up, right? Is it going up or down in here? Is both, right? It's down then up, right? So concave up does not tell you about whether or not the graph's going up or down. It just tells you about whether or not it looks like a frown or a smile. There might be something happening in between. It switches, right? Actually, in this little place where I'm smiling, I go from a decreasing function to an increasing function. I change, but it doesn't change my concavity. Yes? Here where I'm frowning, I go from increasing to decreasing, but I stay a frown the whole time. So although concavity does tell you something, it tells you nothing about going up or down. More on this later. We will attack this a little more. Has anyone like business in like a business class or heard this before? The point of diminishing return or returns. Has anyone ever heard that before? The point of diminishing returns? Look, if I'm a company, let's say I make phones, number of units, and profit. Let's say I start making phones, all right? And initially, I'm not making any money. Like, if I only sell one phone, I'm not going to make any money, right? I have to sell more phones to make money. Yes? So I start making money the more phones I make, right? And then maybe start making more and more money, right? And then what happens is, oops, that's supposed to be nice. Go like this. And now I'm still making money, right? But it's not happening as fast. Do you see that? So what happens is this. I have to overcome the cost of making the phone, pay the employees, the infrastructure to build the phones, whatever. So at some point, no matter how much I'm selling, the cost of manufacturing that is going to overwhelm how much money I'm bringing in, right? So in all of this, right, in this entire case, my profit is going up, right? My profit is going up here. So if I were to look at the derivative, the first derivative, you would tell me that the first derivative is what? Positive always, right? All the time on this entire graph. However, look at the concavity. Smile, and then what? Frown is happening somewhere around here, right? Over here, I can tell you that the second derivative is negative. Over here, the second derivative was positive. Do you all agree, if I imagine splitting it up? So the point of diminishing return comes from this. The slope of the tangent line is how fast I'm making money, the rate at which the profit's happening. Okay, the slope initially isn't very good. And then what happens is slope, I'm starting to make money, more money, more money, more money, more money. And then right here, what happens? I hit a point at which I'm going to still get money, right? I'm still going to make money. But now the slope's going to start to flatten out, right? So this is the point at which I'm still going to get return, but it's going to diminish now. It is the point of diminishing return. Make sense? Still making money, just not as fast as I was making money back here. The point of diminishing return. So a lot of business models, they want to know what that point of diminishing return is because they'd like to know where they can optimize that profit. They don't want to make more units than they have to if it's not going to make them the most money. But it all comes down to, in a graph, the second derivative being 0 is what they really want. Okay, I think I've lullabied you all to sleep. So let me do this. I'm going to ask you to watch the video for 4.3, okay? Make sure you watch the video for 4.3, the one that I do before we come to class. And I'm going to hit 4.3 pretty hard, and we'll get into 4.4. And let's see where that puts us on our schedule here. Today is the 12th. Yeah, this will be great. This will be great. So yeah, watch 4.3. We're going to hit 4.3 on Monday. Do a lot of like problems. I didn't do any. I just want to get you introduced to the geometry of it. 4.4, you're not going to like. 4.5, you're not going to like. Word problems and graphing functions by hand. All right, everyone. Have a good weekend. Right? Yeah.